Hello everyone and welcome back to day 3 of Countdown to AP Week. I'm even more stressed today, but that's okay because we have a fun stack exchange integral that I found the other day. And yeah, let's get evaluating. If you do hear something that sounds like rain, that's because it is currently raining and lightning. Fun. Anyways, let's focus on the math, shall we? Ooh, that'd be good Physics Friday, lightning, wouldn't it? Anyways, one thing to note with this integral with this nice natural log in it is that we can express this natural log in terms of a series. Namely, that natural log of x plus 1 is just equal to the sum from k equals 1 to infinity of negative 1 to the k minus 1, x to the k, all over k. And although this might not look like the nicest thing in the world, especially when we combine it with the integral, it actually does simplify quite a bit into something quite, at least in my opinion, something a little bit satisfying. So subbing this in, what we find, I'm just zoom out real quick. What we find is that our integral is just equal to this, integral from 0 to 1, of course. That's a nice integral sign, my goodness. Of, let's see, the sum from k equals 1 to infinity of negative 1 to the k minus 1 over k, and then times x to the k, whoopsies, to the k minus 1 dx. And the reason it's k minus 1 is just we have this x in the denominator right there, and we just subtract 1. Exponents. And what we're going to do next is just swap the order of the integration and summation, as we usually do. So what we find is this is just equal to the sum from k equals 1 to infinity of negative 1 to the k minus 1 over k. So nothing's changed there, but we just have this integral from 0 to 1 of x to the k minus 1 dx. Which, if you just kind of look at, really is not that bad of an integral. The actual integral bit of this integral is not that bad, whenever you expand it with the summation, of course. Because we can just use, reverse power rule as per usual on this thing. We find that this is just 1 over k times x to the k, but then evaluate from 0 to 1, well, 1 to the k is just always 1, and 0 times anything is 0, of course. We're not doing limits here, so that's true. But this is just equal to 1 over k, meaning that our summation is just the sum from k equals 1 to infinity of negative 1 to the k minus 1 over k squared. And now you actually might recognize this function right here, and that's because this right here is just eta of 2. Do I know eta of 2 off my head? Before making this video, I did not. I do now, but that's not the point. We're going to be evaluating eta of 2 to make this slightly more interesting and slightly longer than the 3-minute video. I actually debated a couple of methods to evaluate this integral. So the first way the summation eta of 2. The first way I kind of went about it was just doing complex analysis with it. So you can use this, you can take the summation and basically calculate it using the sum of residues using like 1 over k squared, because you can do things with cosecant, and I'll probably do a video with that in the future. But that is quite long and a little bit annoying. So the second way I kind of thought about doing this is with using the relationship between the eta and the zeta function. Because, well, you'll see why in just one second. So we know that, just in general, eta of like s, say, is equal to 1 minus 2 to the 1 minus s. Let me just scoot the camera over. 1 minus 2 to the 1 minus s times zeta. If I can actually write a zeta. Oh no. There you go. Oh my goodness me, I cannot write a zeta. There we go. Zeta of s. And if we plug in 2 here, what we find is zeta of 2 is equal to 1 minus 2 to the, 1 minus 2 is just negative 1. So that's just a half. Times zeta of 2. And then this right here is just equal to, this right here is just 1/2. Meaning that we have 1/2 times the sum, and then just by definition of the zeta function, of 1 over k squared from k equals 1 to infinity. And I suppose if I wanted to make this video much longer, like say, 20 minutes, I could do this using complex analysis again. But I don't think there's a need, and that's really just because, well, if we look at the sum right here, that's just Euler's famous sum. That's the solution to the Bessel problem that he formulated in, I don't know the year, but that's just that's just zeta of 2. That's the solution to the Bessel problem. That's just pi squared over 6. So we have 1/2 times pi squared over 6, which is equal to, well, just pi squared over 12. And that right here is actually just our answer. This is just zeta of 2, which is actually kind of funny and unironically just half of zeta of 2. And the reason I say ironic is because the only difference actually is, well, you just have a little -1 here. So it's almost as if like that just like halves it. Which like it doesn't, because, well, it doesn't work for every single identity, as you can see there. But anyway, I thought this was just kind of a little interesting thing. I'll probably make a video in the future, actually, basically going into more summations with residues. That'd be a lot of fun. But for now, we're just going to stick with a nice pi squared over 6, and I'll stop rambling. And thank you all for watching, and see you in the next one.